you all for coming. I know the first slot of the second day can sometimes be a little bit tough for a conference, so I'm excited to see how many people are here and interested in hearing about how unified observability pipelines work. So as Bridget mentioned, my name is Aditya, and I work on the observability team at Stripe, primarily on our open source monitoring and observability tools, which you'll see in a moment. At Stripe, we provide a simple unified API that enables businesses of all sizes to accept payments online. Today, I'm going to tell you about how we've built and how we're continuing to build a unified tool for full cross-sectional visibility into all aspects of your system's code. Now, if you're a big company like Google or Twitter, you can create your own integrated tool that handles all of this for you. And Google has done that. But for the rest of us, we're probably relying on open source or third-party vendors for at least some portion of our monitoring tools. And it's hard to get fully integrated cross-sectional visibility into your code if you're using multiple tools, because there'll always be gaps in between them. Fortunately, though, there's a way that companies smaller than Google can get this level of visibility without writing their whole stack from scratch. And the secret there is all in the metrics pipeline. So I'm here today with one goal: to inspire you all to take control of your metrics pipeline. And not just any pipeline, but an intelligent, context-aware pipeline that can help you achieve the pinnacle of system observability. Some of the stuff that I'm going to talk about already exists today in our open source tool called Veneur. Veneur is our take on an intelligent metrics pipeline, but it's not the only one. And some of what I'm talking about is what we'd like it to become. And that's the exciting part. You can help us all out with that. Because we want to make intelligent metrics and observability pipelines like Veneur the gold standard for observability across our industry, and to make that gold standard accessible to companies of all sizes. So how many of you have ever been on an on-call or pager rotation? Yeah, DevOps days probably like most of the room. Is anyone on call right now? That's like a lot more than I was hoping for. So if I like hear just, like a phone go off and suddenly like people are like darting out of the room, I'll know it's not just like, you hate my talk or something. So I'll tell a story that may be familiar to some of you. It's 3:07 in the morning and you're happily asleep dreaming, and suddenly your pager goes off. Now you want to get back to sleep as soon as possible, but obviously you have to fix the problem. So you need to figure out what's actually going wrong. So what's the first thing that you do? Any ideas? Yes, how do you do that? Sorry, someone said, see if there's a real problem. The answer is yes, how do you do that? I heard someone say a dashboard, which is, yeah, probably what most people would do. You pull up a dashboard. So here you go, and you see that API success rate has dropped just below a threshold. There's a little dotted line. You may not even be able to tell. But all right, so our error rate has exceeded our SLA, which means that there is a problem. But why are our requests failing? For all we know, maybe there's a badly written web crawler which is generating 404s. So to investigate that, we have to pull up another dashboard. And all right, here we can filter by an arbitrary database shard and a country combination, and we see that there are some sporadic but consistent requests that are timing out. And so some requests are failing, but we don't know why they're failing, and we don't know how widespread it is. All we know that it's in the US, this particular database shard is having issues. So we could just spot check more database and country combinations, but that gets really cumbersome. So we go to another dashboard. And this one shows us by server. All right, so now we're looking at across our entire cluster, and we see that 4 boxes or 4 pods are having issues, and the rest are fine. So this is good. Now we get a sense of just where this problem is shaped. Now graphs like this are efficient because they pre-aggregate data. We define the axes that we care about in our instrumentation using tags like country, database shard. And then that's aggregated at runtime, not at query time. So graphs like these are therefore very easy and efficient. They're quick to pull up. But we want to be able to de-anonymize our dashboard data. We want to know things like the types of requests, the users, the HTTP method. And we can't count all of those axes because the cardinality is too high. There are too many different axes for us to actually aggregate all of those at runtime. We need to do some of it later on. We can explore arbitrary dimensions in our data using our logs, but then we have to take the time and the effort to actually interact with them, because logs are not pre-aggregated. We have to figure out how we want to search and query them. So it turns out that this exact regex right there will match only requests that take 30 seconds or longer, regardless of what format they're specified in, whether that's 90s or 1M2s. Like, it will actually match that. I double-checked it. It's hard enough coming up with that when the pressure's off, but imagine, trying to do that when it's in the middle of the night and your servers are down and trying to figure out what's going on. Like, no one really wants to do that. When you've been paged for an outage, you want to have quick and ready, readily available access to that. And of course, our logs are always going to be slower than our pre-aggregated data because it's extracted at query time, not at runtime. So they let us look at arbitrary data, but they're always going to be slower. Fundamentally, though, they are different views on the same data. You just have to reconstruct each view independently instead of being able to go straight from one to the other. And oftentimes, you're going to just end up poking through individual log lines anyway, unfortunately. Because, how many of you have ever written log lines that look like this? No one? Yeah, no. You can admit it. It's OK. I have. Like, I'm making it look a little silly here, but when you think about it, most uses of logs actually do follow this overall pattern, where you're basically saying, all right, I'm about to do a thing. Now I've done a thing. All right, now I'm finished doing the thing. Like, you don't actually care about the text of the logs in this case when you think about it. Like, about to query object, that doesn't mean anything. It's just a way of disambiguating that particular log line from all the other ones so that you know that that particular line of code was executed for that object ID compared to others. And so when you think about it in that light, you realize that you're just using logs like a runtime debugger. It's GDB, but by human. And so reading the logs to figure out the source of a bug is really just one step away from saying, you should read the source code to analyze it and figure out where the bug is. Because logs are really just developers talking to themselves. They're like, hey, I reached this part of the code. OK, I'm still here. I reached this other part of the code. All right, now I'm still here. Like, pay attention to me. That's really just what logs are. Like, I've gone so far as to say that you actually should never really be looking at your logs. If you ever actually need to look at your logs, that means that something is wrong. It means that there is a gap in the rest of your system's observability tools. Now, one other tool for filling in that gap is request tracing. For those of you who haven't used it, request tracing, it's a very fancy term for a fairly simple concept. If you've ever looked at a stack trace or a profile of your program to see which functions are calling which and how long they're spending, that's all request tracing is. The only difference is that request tracing shows you that across all servers simultaneously, if for a single request that needs to touch multiple servers before returning a response, you get all of that, and hopefully color-coded by which server they're on. So you can see here that the green, the purple, the blue, those are all different servers, but those functions are just calling each other. So OK, you've gone to another tool. So now you've looked at 5 dashboards across 3 different tools just to solve the problem, and you may not actually have gotten any closer to it, because if you're lucky, you have tracing instrumented around the code that's breaking. But you might not. And even if you do, it's still not wholly integrated with the dashboards that you were just looking at. Now, in physics, all matter is built using certain fundamental particles. We have electrons, we have protons, and we have neutrons. And everything we see, everything in the observable universe, is built using these fundamental physical particles. And in observability work, our tools are also built using certain fundamental particles as well. We have metrics, we have logs, and we have request traces. Now, the challenge with metrics, as we saw, is that there's no context. They're pre-aggregated, so they're efficient, but they lose their context. With logs, we have the opposite problem. They're not pre-aggregated, so they're not as efficient, but they do have everything. But they're hard to aggregate. And request traces, they require careful planning so that you actually know that you're instrumenting the code that you need. And that's actually not unique to traces, because that's shared with all observability tools. Because monitoring information is really only going to be useful if developers have put in the time and the effort to predict. And not just to predict, but to correctly predict which parts of the code are most likely to break, and what information is going to be needed to debug that code from a broken state. You can think of it like tests. It's relatively easy, usually, to write a test case for a bug once you've already identified the bug. But it's much harder when you're writing code the first time around to predict all of the possible failure modes, all of the edge cases, test all of those, and ship that to production the first time. If you think that you can do that, come talk to me, because, man, have I got a job for you. Metrics are like tests, but higher stakes, because you pretty much only ever care about your metrics when things are already going wrong in production. And this is why one of the main reasons why they say that the people who write a service should be the ones who are on call for the service. It's not a punitive statement, it's just a practical one. The people who write the service are the ones who have the context necessary to, to predict that and then to use that information and debug it correctly at runtime. And I mean, this is a really weird philosophy when you think about it. Like, imagine if we applied that to other forms of engineering. Imagine if we built houses this way. If we built houses the way that we build software, the builders would never be able to leave your house. They would have to stay there and operate every single door and light switch for you. And if your light bulb goes off, fuses in the middle of the night, you'd have to call up the architect and he'd send someone over to, go look, collect some data and say, yeah, it looks like your light bulb is fused. And then he'd have to, get the stepladder and change it for you. It's ridiculous. We don't accept that for any other forms of engineering, so we shouldn't accept it for software engineering either. And this is what observability means. This is what observability is all about. It means designing the interface to facilitate operability of systems at runtime by anyone, not just by the people who actually wrote the code in the first place. So let's say that we're writing a really basic web app. We just need to fetch and return objects from a database. But of course, we want to observe this. It's a very important function. So we want logs, we want metrics, and we want request traces. Let's say that our database client is tracing aware, so we can actually pass it in and get, get that stack trace from the client as well. So how would we instrument just this very simple, 3 lines of code? Well, if you want all 3, you'd end up with something like this. So what are we doing here? We first start off, we set up, a trace for the stuff, then we do the stuff, then we emit a metric for the stuff, then we log the stuff, then we set data on the trace span, and then we finally return the stuff. We're tagging the metric with the axes that we want to pre-aggregate at runtime, and then we're logging the rest of the parameters, which are just too numerous to, but which we might still want access to later. Who wants to write code that looks like this? Right? I hope not. This is very boring. This is so boring that I almost even didn't finish putting together this slide for this talk. That's how boring it was. So if I can just barely be bothered to put together a slide demonstrating how boring it is for a talk, there's no way that we can expect developers to go through this whole song and dance everywhere in their code anytime they do absolutely anything at all on the vague hopes that that data might be useful in debugging a production incident. At most, we can expect that they would remember to write 1 line for instrumentation to observe their code. And even that's not enough, because if they have to sit and think about which one will be useful, then we failed them. If they have to think, I want a metric here, and I want to tag the user, and I want to tag the country. Oh, wait, no, the cardinality, that's too high, so that needs to be a log line. No, that means we failed them. It means that we have failed to design a system that's architected for observability. So let's think for a moment. Why are these all separate libraries? Well, they're separate libraries because the storage and query infrastructure is different for each of them. And it's different because of performance. Because in order to actually efficiently emit, store, and query these different types of data, we need radically different storage and underlying implementation mechanisms. Because statsd and Graphite isn't capable of handling the load that we need to send it to give it our log volume. And Elasticsearch, it's not set up to index data the way we need in order to get request-level traces. But we're engineers. We know that implementation details should never dictate the way that we interact with something, because that's a recipe for bad usability, just as we saw a moment ago. So there are 3 types of data that we're sending: logs, metrics, and traces. And if you squint, they're really not all that different. Like, we could really just emit all of our log lines as statsd metrics with the log text as the metric name, if we didn't worry about performance. And when we structure logs, we're just creating key-value pairs, which are essentially statsd metric tags. And traces are basically like metrics as well. The only difference is that they're aggregated in a special way. We're tagging it with the trace ID and the span ID and the parent ID, and we have to do a special graph-level inner join on those to reconstruct the call tree. But they're fundamentally not that different in terms of the shape of the data. So what if we just had a single interface for emitting all of these? And we could decide later on how to handle and how to represent them. So I call this my I want a pony slide, because I don't just want 1 pony, I want 3 ponies. I want metrics, I want traces, and I want logs. I want all 3 all the time. Well, it turns out we can do this, Because at Stripe, we're in the business of making simple, unified APIs over complex legacy systems. And we're in control of our data ingress. We can have an intelligent pipeline that operates on this full fire hose of data. From our service, we emit a single particle of data, which contains the union of that information. At Stripe, we've dubbed this the SSF. It's our standard sensor format, or when we're feeling a little bit cheeky, it's our sensor sensibility format. All we have to do is make this easy and convenient for the developer to emit all this information with just one short line, and then our pipeline can determine how best to aggregate and synthesize that particle of data. So this is just an example. It'll look a little different in different languages. I don't even remember how many lines that the previous one was, but you can obviously see here it's a lot shorter now. We've combined the metric name and the log name because they serve the same purpose. And previously, we were tagging the metric with the success Boolean and logging the query parameters, so we sent them to different places. But here, we can put all that information in one place and not worry about which will get pre-aggregated and which won't. We can let the pipeline handle that decision-making for us. So Veneur will take a stream of SSF particles for us, and it decides not just where to route them, but also what to make out of them. Each particle here contains the full amount of information, but each icon is telling us what Veneur is going to use it to build. So Veneur takes that SSF particle right here, that first one, and it emits both a log line and a statsd metric from it. This next one here, it was about to do the same thing, but it noticed that the dimensionality of the different tags it was being given was just too high. So it drops the metric, but it still keeps the log, so we still get access to some of that information. And then, this one gives a log and a trace, and then these three are interesting because it gives us a log and a metric, but it also is smart. It notices that these three pieces of data have the same shape, so it's also able to extract a histogram from that and give us a derived metric. It tells us, here's what the shape of the aggregated data looks like as well. So we're not going to send our full log data to Datadog or to Graphite, and we're not going to send all of our tracing data to Elasticsearch, but we know which SSF particles were used to build our histogram because we're the ones who are building that with our pipeline. So if we want, we can record that relationship. And that allows us to integrate our monitoring tools together much more effectively. And that's the crux of it. Veneur and intelligent observability pipelines are not a replacement for any of these tools. They're pipelines that let you integrate them together and leverage them even better. Veneur will use the SSF particles to build the data that tools like Papertrail, Elasticsearch, Grafana, Datadog, Zipkin, OpenTracing, all those tools will present for us in a usable form. And the developer no longer has to decide at the time that they're writing the code how they want to see the data represented when they ultimately will be operating it. They just need to make the decision to instrument it, and the pipeline handles the rest. So let's see some examples of what it means to be able to leverage these tools together more effectively. We can get some integrated views. So going back to the beginning, before we had this graph that showed request timeouts, and we could filter by the fields the metric is tagged with, but we couldn't de-anonymize this data. We had to manually reconstruct the log search term that corresponded to more or less what we were seeing here. And that's painful and inconvenient. If you asked me to do this again, I probably wouldn't be able to come up with that regex. But remember, we own our pipeline, and our pipeline is aware of the relationship between these metrics and the logs because they're emitted from the same SSF particle. So we can layer our own extensions on top of these tools that allow us to link back and forth. So that link right there, which we've added, that will bring us to the corresponding view in our logging system. And it'll automatically construct the exact query that corresponds to the data that we currently see there. So again, it's not a different tool altogether. It's just an integration between the existing tools that allows us to leverage the powers of each other combined more effectively. Another example is in how we make trade-offs with our observability tools. In general, we have to trade off between accuracy, precision, and performance. That's a fundamental property of engineering observability at large scale. We can't do away with that trade-off, but we can ensure that the trade-off works in our favor at each step. And aggregation is a good example of this. Let's say that we're analyzing API latency. You're not going to look at the latency of every single individual request. That's just too much data to, even as a human, you couldn't actually make any reasonable sense of it. So when we look at it, we analyze aggregates. We think of things like averages or medians or the 99th percentile. Those are indicators that capture some of the qualities of the data, but they're lossy. They don't give us the full shape of the data. They just give us the general shape. But even if we have a trade-off, the point of an intelligent pipeline is that we can stack the deck in our favor. And we can ensure that if we do have to drop some parts of the data, we only drop the parts that we don't need. We can make those decisions more dynamic. We can push them closer to the code and make them work in our favor. So let's see an example of how an intelligent observability pipeline helps us make more intelligent trade-offs. Well, we have an availability issue. If our observability pipeline goes down, you're hosed. You don't have any visibility into your system. So our pipeline needs to be highly available. So we use a distributed and tiered architecture. Every single box in the fleet runs its own copy of Veneur. So that gives us a nice property, because as long as the box is running, that means that we know it has the ability to report its own data. In a Kubernetes world, each box here is actually a pod that runs the application container and a sidecar container. But this gives us now an aggregation problem, because if we want the average latency, we just have to collect all of those latencies, average them together individually, and then send those averages downstream, and then we can average them together, because averages work like that. Unfortunately, percentiles don't. Medians don't. You can't combine medians. They're not monoids. There's not a mathematical operation that will allow you to take the median of medians and give you like a valid result about the global set of data. It's just not possible. So if we wanted to get a global percentile, we'd have to send all the data to a global box to be aggregated, which defeats the whole point, because now we've reintroduced a single point of failure. If that global aggregator goes down, we're stuck. But we've also introduced a load problem, because now we have to send all of our request latency data to a single box, and that's a lot of data. With Graphite, way back, we actually were running Graphite, and we tested this out. We ran as just we ran a single heartbeat metric that we sent downstream to our global Graphite instance, and we found that we would drop like 50 to 70% of our heartbeat metrics on the floor because it was just overloaded. So to solve this, we use, as I said, a distributed and tiered infrastructure. We use a consistent hashing scheme, so we have a number of different aggregator boxes that will run in parallel, and we use a consistent hashing scheme to ensure that all of the different metrics of a given kind that need to be aggregated together will get sent to the same box. So the host 1 will always send the red metric to the first one, the blue metric to the second one, et cetera. And hosts 2 and 3 will also always send the red metric to the first and the blue to the second, and so forth. This means that we can horizontally scale our aggregation, and we can also ensure high availability, because if any aggregator box goes down, that's fine. We only lose the aggregates on that one box. The other n-1 are fine. But we can actually do better than that. Now, my background's as a statistician, so this here is the stuff that I could easily spend an hour talking about. And so if you want the full picture, come find me at one of the breaks, and I'll be happy to go into more detail. I'll just give you a taste, though. I said a moment ago that there's no mathematical operation that you can do, mathematically valid operation you can do that will give you the median of medians and give you a meaningful result. And that is true if you're dealing with exact operations. But we can actually use approximations to calculate our percentiles, as long as we're confident that those approximations have the exact properties that we need. And it turns out that there is an algorithm, the tdigest, which do have the properties we need. It allows us to calculate recursive percentiles in an online fashion. So it means that we can operate on streams of data, not on loading all the data in memory, and we can calculate percentiles on each box individually, then send those percentiles downstream to be aggregated, and then we just run the same algorithm there again. We operate on the percentiles as if they were the raw data. Tdigests allow us to trade off variance in the medians for precision in the tails. So if you look at this error chart right here, you can see that there's like a decent amount of variance in the median. It's not bad, but it's not great. But once you get to the tails, it's actually pretty precise. In fact, you might be dealing with the exact values at the tails. And that's what we care about, because oftentimes when you're looking at latency, you don't really care so much what the median latency is, as long as you're bounded by the tail end latency. So again, I won't go into too much detail here, but if you're interested in how some of these, how we make some of these trade-offs and how some of these more sophisticated algorithms work, come talk to me afterwards. So let's go back to that story at the beginning. It's 3:07 in the morning, you're paged, you're still not thrilled about being woken up, you're never going to be, but that's okay, because you know that your systems have an intelligent observability pipeline which can do that heavy lifting for you. You don't have to worry about whether the code that you're actually debugging was instrumented, whether the developer actually took the time to think about which pieces and which types of data that they wanted to add to it, because you know that it was easy for them. You know that they only needed one single interface to instrument all their code, so you're confident that you have the proper visibility into your code. And you don't need to tediously reconstruct each separate view of the underlying data because your tools are integrated. Your pipeline allows you to preserve those relationships and jump back and forth between them instantly, between those equivalent views, without having to come up with them again from scratch. So you're able to locate the source of the problem quickly. You're paged at 3:07, by 3:09 you fixed it, and by 3:11 you're back asleep. If you think that sounds like a better story to be living, try Veneur out. It's free, it's open source, it's on GitHub. We built the first version of Veneur ourselves at Stripe, but we're not the only ones who use it or contribute to it. Sentry and Bluecore are two other companies that have monitoring and runtime data right at the core of their products, and they both rely on Veneur for their metrics pipeline as well. If you're currently using any of the most common tools like Grafana or Datadog or SignalFx or Prometheus or OpenTracing, then Veneur can work out of the box for you. You don't have to do anything. It's just a drop-in addition or drop-in replacement. You don't have to change any of your existing instrumentation at all. To get the full benefits of Veneur like we talked about today, you'll probably want to start using instrumentation like the SSF, but as a start, Veneur is capable of working with your existing setup. We run on a six-week release cycle, and we do provide native support for Kubernetes for those of you interested in that. So take a look. Through our work and through the help of others, we've achieved a lot with Veneur already. But as I said, there's a lot of work left to do if we want to make intelligent observability pipelines universal and the gold standard across our industry. So let's do this. Let's make the gold standard of observability, which is fully integrated observability tools, accessible not just to the Googles of the world, but to hobby projects and to companies of all sizes. Thank you.